The Fast Fourier Transform, or FFT, drives nearly every digital interaction you have. It processes the signals in your Wi-Fi, compresses the audio in your streaming music, and filters the noise out of your phone calls. If you want to understand how this algorithm actually works, almost every textbook will tell you that mastering Leonhard Euler's mathematics is the absolute prerequisite. That advice usually traps people. Euler was prolific, and he invented entirely separate branches of mathematics that course materials routinely lump together. On one side, you have Euler's geometry, the mathematics of physical shapes and topology. On the other side, you have his complex analysis, the mathematics of waves and vectors. If you choose the wrong path, you will spend weeks studying topological proofs that offer zero help in writing or reading FFT code. To avoid that trap, we need to audit Euler's work using a strict return on investment framework, specifically optimized for learning the FFT. This chart measures two things. The horizontal axis tracks our primary goal, how directly a mathematical concept applies to the FFT algorithm. The vertical axis measures the cost, the sheer amount of study time and cognitive bandwidth required to actually learn it. By mapping the topics here, we can strip away the historical bloat and isolate the exact mathematical mechanics required to command the algorithm. We start in the lowest ROI territory, with Euler's characteristic for polygons and convex polyhedra, which earns a 1 or 2-star rating for our specific goal. This branch of math focuses on topology. It teaches mathematical invariants by showing how shapes can stretch or compress without breaking their core geometric rules. That information is critical if you are building 3D mesh renderers or designing CAD software. We also see it used in medical imaging hardware. Looking at the physical structure of an MRI machine, engineers use spatial grids based on this geometry to organize the raw physical data before they ever apply a 3D FFT. But if your goal is to learn the mechanics of a standard 1D or 2D Fourier algorithm, understanding shape invariants gives you no mechanical advantage. It is a time-consuming trap. Moving up to the 3- and 4-star topics, we find Euler's work on the sum of exterior angles. Angles are the prerequisite for the unit circle, and the unit circle is the mathematical foundation for sine and cosine waves. Every single basis function inside the FFT relies on these angles to determine its frequency and phase. You cannot process a signal without them. However, as this animation demonstrates, a smooth geometric sine wave does not map easily onto rigid discrete data points. Knowing the geometry of a wave does not explain how a processor efficiently calculates it. Trigonometry acts as a conceptual bridge. It is strictly required, but stopping here leaves you without the computational engine that makes the algorithm fast. There is one 3-star exception in Euler's geometry that deserves our attention: his formulas applied to curved spheres. Applying Euler's logic to curved geometry leads to spherical harmonics, the 3-dimensional analog to the Fourier series. This image of Earth highlights the exact macro-scale surfaces where scientists apply this math, running Fourier analysis on global weather models and planetary data. Similarly, astrophysicists use it to analyze cosmic phenomena, as seen in this heat map of the cosmic microwave background, tracking energy fluctuations across the universe. But unless your specific career involves mapping planets or deep space, spherical harmonics are an advanced detour that will drain your study time away from standard digital signal processing. That brings us to the 5-star apex of the matrix, Euler's complex analysis. This entire field rests on one non-negotiable equation, Euler's formula, where e to the I theta equals cosine theta plus I sine theta. This equation does what trigonometry couldn't. It packages sine and cosine into one rotating vector in complex 3D space. Notice it pauses at evenly spaced intervals. These roots of unity are the exact tool the FFT uses to slice data. Learning to calculate with imaginary numbers creates early cognitive friction, but this formula is the exclusive engine powering the discrete Fourier transform and the FFT. It provides the highest possible return on your study time. Based on this ROI audit, your learning roadmap breaks down into 4 sequential parts: geometry, trigonometry, complex numbers, and Fourier math. If you are a time-poor pragmatist, a coder who needs to implement an FFT immediately, You need a ruthless approach. Skip parts A and B, jump straight into part C to learn polar forms, and proceed directly into the roots of unity in part D. Alternatively, if you are a deep dive optimizer, perhaps a graphics developer or a student who requires complete spatial mastery, you have a different route. Dedicate roughly 20% of your schedule to Euler's geometry to build your structural intuition, then apply the remaining 80% to the heavy calculations in parts C and D. Euler's topological invariants are fascinating mathematics, but to actually build, command, and deploy the FFT, you have to master his rotating complex vectors.